after you pour in milk and it disappears.
Any equation.
Okay, so this time we've got water flowing into a cone. And the top of the cone is going to be 16 centimeters, and when you're at the top of the cone, the radius is going to be 4. So we want to know at and the water's coming in at 2 cubic centimeters per minute. How fast is the water level rising when it's at 5, 10, 15 centimeters deep?
It's going to slow down as it fills.
This is tricky.
All right, because now what's changing at a constant rate this time?
The
What is it?
Y.
Not the y.
The radius.
H.
Not the radius.
The volume.
The volume is actually changing at a constant rate. So that's actually good because you don't see any V's up here, all right? But that means that I have to come up with a relationship that involves volume, right? And that's actually going to be easier for us. So if we take a look at this thing and as it fills, right? Now it's filling at a constant rate, but now there's a couple other things that are changing, but they're not at a constant rate. H and R. Look, that radius really slows down as it goes up, right? At the beginning, it's like it's just getting bigger and bigger, and then it just kind of really starts to slow down. Same thing with the height, because since it's wider at the top, I have more surface area to cover every time I dump some volume in there, right? So this one I think is a lot easier to see that the rates are changing as it gets bigger. Okay, so we need to come up with our relationship this time. It's got to involve volume. That kind of gives it away.
It's the equation of volume.
All right, so we need volume of a what? Of a cone. Anybody know it? Anybody know the volume of a cylinder?
It's half of that.
It's not half of that. It's actually 1/3 of that.
Oh, yeah.
You ever seen that experiment done? You really don't believe it until you see it, where somebody has a cylinder that has like a certain radius, and then they have a cone of the same height with the exact same radius in it. And if you take sand and you fill up the cone with the sand and dump it into the cylinder, it takes exactly 3 of them. But it doesn't seem like it should fit.
Yeah, you think it's too much.
It seems like it should be way too much, but it works perfectly.
Yeah.
All right, so this is going to be, but that's the same thing for any kind of pyramid as related to its prism. Right, so if I have a square-based, a square-based prism of a certain height, then if I have a pyramid with that same base of the same height, it will be 1/3 of its volume always. Right, so that's kind of a way to remember it. Right, but you're going to face cones more than anything. All right, so the volume is going to be 1/3. All right, now how do you find the area of the big base here? Because it's in what kind of shape? Circle. So that's pi r squared, and then times the height. All right, now, what's already kind of scary about this? Pi is not scary.
It's a number.
It is delicious though.
How are you going to find R and T?
Well, how does this differ from any of the other problems that I had?
It's just different. There's no X's.
Yeah, no x's or y's, but everything's changing with respect to time. But before I only had 2 variables. How many do I have this time? 3. All right, so I'm going to have to get rid of one of them. Which one do I know has to stay?
V.
The V has to stay because they gave me that one. They gave me the rate that the volume is changing. So I know that that one's got to be a keeper. Right, so it's either got to be R or H. Why do you want to get rid of R?
Because you have H.
They gave me the H because we're actually trying to find how fast is the water level rising. That's H. So I got to keep H because that's what I'm actually being given. I'm given H's. All right, so R's got to go. So now I need a relationship within my relationship. I need a relationship between R and H. Yikes. Not area.
No.
All right, now one of the things that I don't have labeled in here, which we can do, is we know that from the bottom to the top of this thing is, what did they say? The height is 16. And we know that at the tip top, the radius of this thing is 4. Not just one. What about them? What else? Now you got to think way back into the depths of your geometry knowledge. Geometry chapter 8.
Is that a right angle up there?
What's that? Yep, it sure is. So is this.
30, 60.
No, you can't count on that. But I do know that those two are both the same. And I know that they both share this angle.
They have a ratio.
So they have two angles in common. What does that mean about about the little triangle and the big triangle?
The ratio.
They have a ratio, like there are, there's another word for that. So this ratio, when one ratio is equal to another ratio, we have a word for that.
So
It rhymes with proportion.
Proportion.
Yeah, I couldn't think of anything. So yes, it's a proportion, right? So this would be my H and this would be my R, whatever they are, correct? Right? But we know that this is never changing. So R to H is going to be in the ratio of what? 4 to 16, because I went top to side. So up here I got to go top to side. So that means that my R to H is really a 1 to 4 ratio. Now what do you do with proportions? Almost always.
Multiply them times
How do you multiply them?
whatever variable you have.
No. Remember, I want to get rid of the R, so I need to solve for R here so that I can substitute. You guys are thinking way too high. When you have two fractions equal to each other, what do you want to do?
Okay.
Kurt, we need you.
Kurt would be singing some kind of song.
What do you do when you have two fractions equal to each other?
Because we don't have
You
a
guys
proper
always
key.
want to do it. Yeah, half the time you guys want to do it when you're adding two fractions together, for crying out loud.
I'm so tired.
All right, so if I cross multiply here, I'm going to get 4R
Power key.
equals H. I don't want H alone, though. I want R alone, so what do I do?
Plug in that by 4.
Divide both sides by 4. So R will equal H over 4. So everywhere I see an R, I get to put an H over 4 in for it. That's going in right there. So now my volume is going to be 1/3 pi times H over 4 squared times H. All right, and let's clean that up a lot. Right? This is really like a pi over 1, right? I'm going to let everything be a fraction. When I square H over 4, what are you going to get?
8 squared over 16.
Yep. And then this is like an H over 1. So when I multiply everything across, I'm going to get V equals pi H cubed over 48. And if you want to make life easier on yourself, that's really a pi over 48 H cubed, because that's going to be a heck of a lot easier to take the derivative of.
Can't do that.
Oh yeah, you can. No, I don't even have to change. I would have to change, or I would have to product rule this, or quotient rule
Pi over
this.
48.
But because I'm going to let pi over 48 be my coefficient,
Oh.
it's going to be way easier. All right, so now I finally have something with two variables, which was the goal of all that craziness. So I could finally start taking the derivative of this thing with respect to t. So when you take the derivative of v with respect to t, what do you get?
Pi over 16.
No, just this. I'm on the left side only. Come back with me, to the left. But because it wasn't a t, dv over dt. But you're right, I get 1 dv over dt. All right, equals, all right, now when I take the derivative of this other side, right, because I'm going to I'm going to bring 3 across, so 3 pi over 48 h squared, right, times dh over dt. And we know that that's going to simplify to pi h squared over 48, not 48, that's simplified, so 16 dH over dt. All right, now I can start filling in some of these things. Which one am I solving for? No. I want how fast, that's the rate. So what's the rate? The water level's rising. So the rate of H. So I want this one. That means all the other things I need to be able to plug in for. What's the easy one? No. Well, I guess it is. So we're going to find the first height. So when the height is 5, that's my H. What's the rate of the volume that the volume is changing? 2, because that was this one. Now you just get dH over dt alone. By? That's the same thing as multiplying by 16 over 25 pi. So I'm going to get 32 over 25 pi. And that's my dH over dt, whatever that decimal comes out to be. (32) divided by 25 pi. 0.41, and that was in what? Centimeters per minute. Nope, because it's just height. Height will change in centimeters. Now what's going to happen as I put in bigger numbers here?
Smaller.
It's going to slow down because there's more space to fill. Yes?
You just keep that last blue equation and just keep plugging stuff in
What do you mean?
when you want
A new height.
Right. Right. Yeah, you would just use this one, but then I would use my 10 and my 15 in here for my H each time.
With the other one, you have to keep doing that.
Right, because as your R's were changing for that one, so was your X. This one I'm only dependent on one thing. Trying to get these? We're going to practice with these a long time. Like, usually I don't spend over a week in a section, but we probably will this time. Right? Because there's a lot of different things we can do. And I think you guys will get pretty good at the geometric ones for the most part. They're really not that bad, I think, because you'll get used to them. For examples, now you have a whole other sheet of examples. Yeah, well, we've got a ton. Okay, so let me get your homework up here. It's not online at the moment, so let me track it down.